welcome back. In today's video, we're going to talk about the relationship between angles and portions of circles. So we're going to find the arc length of a sector of a circle, which is a piece or portion of a circle. We're going to find the area of a sector of a disk, and then we're going to study the relationship between what's called linear velocity, which is how quickly an object is moving forward or backward, and angular velocity, which is how quickly an object is spinning, and the relationship between those two velocities. For example, if you're riding a bicycle, what is the relationship between how fast the wheel is spinning and how fast the bicycle is moving forward? Circles. So if I have a circle with its center located at this white dot here, and I draw an angle at the center of this circle or disk. Such an angle drawn at the center of a circle is appropriately called a central angle. Now, when we draw a central angle inside of a circle or a disk, we specify what's called a sector of that circle disk. Basically, the pizza slice that that angle cuts out of the full circle or the full disk. Now, what's nice about sectors of circles is that it's very easy to calculate the length of a sector of a circle or the area of a sector of a disk by just using the formulas that we have learned for the circumference of a full circle and the area of a full disk. So let's recall that the circumference of a full circle depends on the circle's radius, depends on the circle's size. The circumference of a full circle can be found by taking 2 times pi and multiplying it by the circle's radius, r. The area of a full disk can be found by taking pi, just pi, and multiplying it by r squared. Now someone says, okay, I don't want the area of a full circle. I only want the area of a pizza slice, a sector of a circle. The circle has a radius of 5, but I'm only interested in the sector corresponding to a central angle of 30 degrees. So if I were to briefly sketch this situation, we have our full circle of radius 5 units, and at the center of the circle we drew an angle of 30 degrees. And they want to know what is the area of this pizza slice sector that was drawn in this circle by this 30-degree angle. So what I'm going to do is this. I'm going to say, what would the area be of this entire disk? The area of the entire disk is given by this formula in green on the right. The area of the entire disk would be equal to pi times 5 squared, or 25 multiplied by pi. Now we don't have the full disk, we only have a fraction of the full disk. Now exactly what fraction of the full disk do we have? We can figure out the fraction of the disk that we possess by looking at the central angle and comparing it to the angle that would correspond to having the entire disk. Now to get the entire disk, we would need a central angle that goes all the way around. The full disk would have an angle corresponding to 360 degrees, a full revolution. We only have 30 degrees out of that full 360. So the fraction of the full disk that we possess is 30 degrees out of the full 360 that would correspond to the entire circle. So if I reduce this fraction The fraction of the full disk that we have is we have 1/12 of the full disk. So because we're working with 1/12 of the full disk, we must also have 1/12 of the area of the full disk. So the area of our sector would be equal to 1/12 of the area 25 pi to 25 pi over 12. Let's find the arc length of a portion of a circle that corresponds to a central angle of pi over 2. The circle has a radius of 3. So to visualize this, the full circle has a radius of 3. We're dealing with a sector with an angle of pi over 2. Pi over 2 corresponding to 90 degrees or a quarter of a full rotation. So they want to figure out the arc length of the sector of this circle, not area, but length this time. They want to know how long is this portion of the outer rim determined by this angle of pi over 2. Now once again I can say, okay, what would be the length of the outer rim of the entire circle? In this case, because the radius is 3, the circumference of the full circle would be equal to 2 times pi times the radius, which simplifies to 6 times pi. But I don't have the full circle, I only have a fraction of the full circle. What fraction exactly do I have? Visually, it may be obvious that I have 1/4 of the full circle, but let's just confirm that mathematically. Under normal circumstances, a full circle would correspond to a full rotation of 360 degrees, or in units of radians, 2 pi radians. Out of those 2 pi radians, we have pi over 2 radians in our central angle. So if I simplify those two fractions, pi over 2 divided by 2 pi simplifies to 1 over 4. So that confirms, yes, we have exactly 1/4 of the full circle. And therefore this green segment has 1/4 of the full circumference. It is 1/4 of the full length, which can be simplified to 3 pi over 2 length units. Now when you're working with central angles that are given specifically in radians, you can come up with a pretty convenient formula to find the area of a sector. And I'll warn you right now, and I'm going to warn you again, please be careful. This formula really does only work when the central angle is in radians. So let's figure out what the formula would be. So in this case, we have a sector of a disk with a radius of r, and we're trying to figure out what the area of the sector would be. So using the same principles that we used in the previous few exercises, the area of the full disk would be given by the formula pi times the radius squared. Now just like in the previous exercise, we can consider what fraction of a disk we would be working with in this problem. We have an angle of theta in radians, out of the full central angle for the full disk, which would be 2 pi radians. So the area of the sector would be equal to pi times r squared multiplied by this fraction theta divided by 2 pi. And if we simplify that by canceling those pi's, we get the following formula. if you want the area of a sector of a disk where the disk has radius r and the central angle of the sector is theta in units of radians, then you can take the radius squared, cut the result in half, and multiply that by your angle. Let's try it again with a sector of a circle of radius r corresponding to a central angle of theta. Once again, theta is measured in radians. Let's see if we can figure out a formula for the arc length of that sector. Once again, we can use a very similar principle. To find the arc length of the sector, let's consider first the circumference of the full circle, which for radius r would be 2 times pi times r. What fraction of that circle are we working with? Well, our angle is theta radians out of a total of 2 pi radians. So to find the arc length of our sector, we just need to take the circumference of the full disk and multiply it by this fraction. 2 pi r multiplied by theta divided by 2 pi. This formula is even simpler than the one that we had before, because not only do the pi's cancel, but so do the 2's. So the arc length of a sector would be equal to just the radius multiplied by the central angle. Once again, I really cannot emphasize enough that these two formulas only work when the angle is in radians. One of the reasons that we have radians, one of the reasons that we measure angles in such a seemingly strange way is because it turns out that quite a few of the formulas that we need as we're working with triangles, circles, trig functions, etc., a lot of those formulas just really work out nicely when we're dealing with angles that are in units of radians. Generally speaking, the formulas work out way better with radians than they do with degrees. Now, for an example of something that you don't want to do, suppose that I gave you the following exercise: sector of a disk, radius 7, central angle 45 degrees, find the area of the sector. This is wrong. What I'm about to show you is what you don't want to do. What you don't want to do is say that the area of the sector is equal to 49, or 7 squared, divided by 2 multiplied by 45. This is not the area. This is significantly larger than the actual area. The problem is that this is an attempt to use the formula given above for the area of a sector, but the angle in our problem is not given in units of radians. If you want to use this formula, you're going to need to take that angle and convert it so that it is in units of radians. The right way to use that formula is to say that 45 degrees, an angle that we have worked with quite a bit in video 2, is equivalent to pi over 4 radians. And this is the real value of theta that you want to use in that formula. The true area is equal to 7 squared over 2 multiplied by pi over 4. So the area in reality is equal to 49 pi divided by 8 if I multiply those fractions straight across. Velocity, the word velocity, is a physics term that is used to measure how quickly an object's position is changing. And if you have an object which is moving in a circle or which is spinning, we describe how quickly the object's position is changing using something that can be called angular velocity. Angular velocity is a measure of how quickly the object is spinning or turning, how quickly the object's angle is changing. So some common units of measurement for angular velocity might be in degrees per second. Maybe something like 40 degrees per second. An object with this angular velocity would be spinning at such a rate that it turns 40 degrees in 1 second. It might be also natural to describe something like 4 revolutions per minute. An object with this angular velocity would be spinning or turning at such a rate that it spins 4 times fully in 1 minute. Or you might say something like 30 radians per hour. In general, if you want to talk about angular velocity, you have some angle unit on the top and some time unit on the bottom. Now, angular velocity is appropriate for an object which is spinning or moving in a circle. But if you have an object which is not moving in a circular pattern, but is instead moving in a line, we can still talk about the object's velocity, but in this case, we talk about what's called linear velocity, which is how fast the object's linear position is changing, how fast the object is moving forward over time. Linear velocity is the kind of thing that we're describing when we say miles per hour, or when we say inches per second, or when we say meters per second. For linear velocity, we have a length measurement in the top, a measurement of how far the object moved forward, and then a time measurement in the bottom, length per time. Now, if you have an object which is moving forward as a result of some kind of wheel, like a bicycle or a car or a cart or wagon or something like that, then there is a relationship between the angular velocity of the wheel and the linear velocity of the object that is being moved by the wheel. So let's go ahead and do a quick exercise to see if we can get a sense of what the relationship is between angular velocity of a wheel and the linear velocity of the object that is being carried by the wheel. For example, a bicycle wheel apparently has a diameter equal to 30 centimeters. Now, just as a quick note, because the word diameter can be tricky, the radius of the bicycle wheel would be equal to only half that. The radius would be equal to 15 centimeters. Now, they're telling me that the wheel has an angular velocity of 5 revolutions per second. So the wheel of the bicycle is spinning at such a rate that it spins 5 times fully around in 1 second. So what then is the linear velocity of the bicycle? If the wheel is spinning 5 times per second, how fast is the bicycle moving forward? Let's give our answer in kilometers per hour rounded to 2 decimal places. Now, the first thing that I'm going to think about is how far does the bike move forward when the wheel spins 1 time? So that we can actually see this in action, I've rigged up a little bit of an animation on Desmos. In red, I've drawn the bicycle wheel, and I've attached to the wheel a purple point so that we can actually envision the wheel spinning and rolling along the ground being represented by the positive x-axis here. And I'm going to use a slider to move and roll this wheel 1 revolution to see how far the object will be carried by that one revolution of the wheel. So here we go. When I roll the wheel, you can see it rolling because the purple dot is spinning. And once the purple dot returns to the top, we have executed one full revolution. And as that's happened, how far of a distance have we traveled? That's indicated by this blue line segment here on the bottom. We've traveled a distance, looks like approximately equal to almost 100, more than 90, maybe 92 or 93. Now I want you to notice something as this wheel completes one full revolution. Imagine that the bicycle wheel is covered in paint, is covered in blue paint. And as the bicycle wheel covered in blue paint rolls forward, this blue line segment on the x-axis will be exactly equal to the blue paint imprint left by the wheel on the ground. Now, how long is this line segment traced in blue paint by the wheel as it rolls out? That blue line segment is going to be exactly equal in length to the circumference of the wheel. The circumference of the wheel is going to be exactly the same as the distance traveled by the wheel in one full revolution. So the circumference of the wheel is the distance traveled by the bicycle when the wheel spins around one time, one revolution. Now for a wheel of radius 15, the circumference of the wheel would be equal to 2 times pi times 15, which would be equal to 30 times pi centimeters. And since pi is approximately equal to 3, this quantity would be a little bit more than 90, which matches the length of the line segment that we saw on Desmos just a few minutes ago. So this would be the length traveled by the wheel in one revolution. So now let's try and figure out how fast overall the bicycle is moving. And to do that, I'm going to do some unit analysis. I'm going to start by taking the fact that the bicycle's speed was expressed in terms of 5 revolutions in 1 second. So now, let's use the fact that in one revolution of the wheel, the bicycle was carried forward by a distance of 30 pi in this case centimeters, because that was the units for our radius. So if we cross-cancel these units of revolutions, we now have the object's linear speed in units of centimeters for the length units and seconds for the time units. So that would be our final answer, except we were asked to give our answer in units of kilometers per hour. So let's go ahead and let's change this so that the length units are in kilometers instead of centimeters, and the time units are in hours instead of seconds. So I've got to get rid of the seconds in the denominator, so I'll counter it by putting seconds in the numerator. I want to have hours down there instead, so let's think about how many seconds, for example, are in 1 hour. There are 60 seconds in a minute, 60 minutes in an hour, so there are 3,600 seconds in 1 hour. Let's also figure out, alright, I've got to get rid of the centimeters in the numerator, so I'll counter that by putting centimeters in the denominator. I want to have kilometers in the numerator instead. So, kilometers in the numerator, how many centimeters are in 1 kilometer? I didn't leave myself nearly enough space, because it turns out that there are 100,000 centimeters in 1 kilometer. So after canceling everything out, cm cancels cm, seconds cancels seconds, we now have a linear velocity whose numerical value is equal to this 5 on the far left, multiplied by the 30 pi, multiplied by the 3,600, multiplied by the 1, all over the 3 ones, and the single 100,000. So using our calculator, let's get a decimal approximation for this. So the calculator reveals that to be approximately equal to 17 kilometers per hour. I think this is somewhere around 10 miles per hour if you're from the United States. So quite a leisurely bike ride. Nothing too unusual, but it seems pretty relaxed. Now, in general, there is a formula that can be used to translate directly between angular velocity and linear velocity without having to go through this full analysis. But do be careful, this is another one of those formulas that really reveals how useful radians are compared to degrees. The formula that we are about to give only works if your angular velocity is being measured in the units of radians per time unit. So if you've got a wheel with a radius of r length units, whatever those length units happen to be, centimeters, inches, miles, kilometers, etc., and you've got an angular velocity of omega, specifically measured in radians per time unit, then what's the formula for the linear velocity? Let's figure it out first, let's reason it through, and then we will state it and you can use it forevermore. So we know that the length traveled per revolution is the same thing as the circumference of the wheel, which for a wheel of radius r would be equal to 2 times pi times the radius. So if I take my angular velocity, radians per time unit, then how many revolutions is this wheel spinning through per time unit? In one revolution, there are 2 pi radians. So using a unit analysis, I can multiply by the fraction that has radians in the denominator and revolutions at the top. Now, per each revolution, wheel moves the object 2 pi r length units. So if I simplify all this, radians cancels radians, revolutions cancels revolutions, this 2 pi cancels this 2 pi, and all that's left for the linear velocity is equal to the angular velocity multiplied by the radius. So to summarize, if you have a wheel with a radius of r and an angular velocity where the angles are measured in radians, then the corresponding linear velocity, which I might call v for short, is given by angular velocity multiplied by the radius of the wheel. I can't emphasize enough, this works for radians only. Now you say to me, Sam, you've already said this 4 or 5 times, we get it, but honest to goodness, there's going to be somebody who on the exam is going to try and use this formula when the angular velocity is not in radians. So as a quick example, we have a wheel with a radius of 0.1 meters on an angular velocity of 3 revolutions per second. Find the corresponding linear velocity, and let's give our answer in kilometers per hour. Now there are a couple of different subtleties here. The first subtlety, which harkens back to this repeated and increasingly annoying warning that I've been given, is that the angular velocity is not being described in terms of radians per time. It's being described in revolutions per time. So if I wanted the true value of omega, for the sake of that previous formula, I would have to take 3 revolutions per second, and I would have to do unit analysis to change that 1 revolution to something in terms of radians. So multiplying through, this would be equal to 6 pi radians per second. Meanwhile, the wheel has a radius of 0.1 meters. So then, now that I have angular velocity in the correct units, I can say that the linear velocity v is equal to the 6 pi multiplied by 0.1. But question, since the units of radius are meters and the units of time currently are seconds, what would be the units of the linear velocity that we've just calculated? The units would be in the length units, meters, divided by the time units, seconds. And they want their answer in kilometers per hour. So although this is numerically equal to the correct answer, this is not yet in the correct units. So let's go ahead and let's take this 0.6 pi, which is in the units of meters per second, and let's convert it to the units of kilometers per hour. Once again, we've got 3,600 seconds in 1 hour, and there are 1,000 meters in 1 kilometer. So if I calculate this with a calculator and round it to 2 decimal places, let's see what number we get. We get an answer which is numerically equal to 6.79 kilometers per hour rounded to 2 decimal places. That concludes today's material. We looked at how angles, as we described them yesterday, are related to some common problems to do with circles and sectors of circles, as well as objects moving in a circular pattern. And really the big takeaway from today is that if we work with angles that are in terms of radians instead of degrees, we unlock the ability to use some really convenient formulas.